Thank you for inviting me, and I hope to give a little bit of experience-based talk to you here today. I think it's interesting to look back because in many respects it always seems to me that I have been a design engineer, but when I was born I wasn't, and so there was a phase of education, and so it become relevant, of course, to look at that education. Because you're wanting to create design engineers who are going to be design engineers in the next 40 or 50 years. And so I think it's interesting, I think, then to see what design engineering has meant to me throughout that time. Now, I've learned a lot of stuff, and as Jeff said in the introduction, my education wasn't exactly easy in the beginning. Because I didn't actually come out of university, my first degree, until 1974. But that, if you like, was the time when I stepped out onto this electronic design engineering role. I didn't know what it was going to be. I didn't anticipate an awful lot. But I knew that at that point, let's say by the time I was nearly 25, it was actually getting a little bit late to start doing higher degrees. I just needed to start earning some money. If you look at the topics that were included in that degree, they're not unfamiliar today. And you can think that in many respects that what we've done, what we've been doing since 1974 hasn't really changed. It's the same sort of stuff. That's kind of relevant today as it was then. Of course, you have to take a look at what electronics was at the time, because when I stepped out into here, this is what your terminal looked like. This is a paper tape, and the paper tape has holes punched in it, and when you submitted a job on the one computer that we had in the entire site, whose performance was probably only about the level of what you're carrying around in your smartwatch today, then this was, a big deal. This we thought was the state-of-the-art technology. Electronics was mostly professional. There was a lot of valves around still. There was very few transistor level products. I remember at this time I bought a Heathkit transistor car radio, because your car didn't come with a radio. And that was added and built, and the thing that was really exciting about it was when you turned it on, it came on immediately. You didn't have to wait while the valves warmed up, because most other things needed to warm up. So larger computers had one computer, larger companies had one computer, and the car and the telephone were still very much electromechanical devices. There was practically no electronics in the home beyond the TV and the radio. The question at that point was I really prepared for the next 42 years as a design engineer? How could I have been? I mean, that's what a radio looked like inside. That was the entire circuit. The 7 transistors in it. I could design a circuit like that. I knew how the transistors worked. I knew how to set it up. And it was an appallingly basic looking product now in comparison to what we expect today. I mean, that was my car, and that is the entire circuit diagram of it. There was no transistors, no electronic anything in there. I mean, these are fairly elaborate illustrations of a bulb. I think otherwise it would have looked very boring as a circuit diagram. And that's what a telephone looked like. They really did wire them up like that. That was the entire circuit diagram. Even in the telephone you didn't have a transistor. Very clever carbon microphone. It's a capsule of finely ground carbon which is squeezed by a diaphragm, and the resistance varies as it exhibits the pressure wave. This rather clever transformer which effectively prevents half of the power from the microphone being absorbed in the earpiece. So it's a 2 to 4 wire conversion. It's very clever. It actually does quite a lot of making a telephone work. And of course this is the dialer with these little holes which actually produces an interrupt basis. So I mean, they're incredibly simple, but this is the state that electronics was in when I stepped out of the education system and was going to be an electronic designer. Now I never had the benefit of anybody telling me this, so I'm passing it on to you now, because it actually cost me quite a bit of effort to learn that design engineering is about making stuff happen. It's actually stuff that finances everything that I do as an engineer. I've got to make something which is going to be saleable to a customer, and the customer has got to want it enough to pay money for it, because then the money flows back down the chain. It pays my salary for the next job, but it also pays the salaries of everybody else who's involved in that food chain, such as the educators as well, because I am the product of an education system, and as long as I'm useful in this role, then the education system will be supported. If the education system is not delivering essentially what businesses need, then it will ultimately find that finances are going to be difficult. So the things that have got to work, they've got to be economical, they've got to be reproducible, they've got to be innovative. People talked about circuits to me, transistors and wires and resistors and stuff like that, but they never said anything about the economics. And that's why I say this is a painful exercise for me to learn, because I thought that in many ways this was what it was about. It was about excitement and challenge and pleasure and personal pursuit, and that's the thing which excited me about the prospects of electronics. In reality, the reality is I've got to do stuff which is going to work. It's promising the future. It's taking a concept and making it happen. So, we haven't always been very good at this. Unfortunately, this predates me. But this is computing in its very early stages. And this was done by Hipparchus in 100 BC. So it's quite a long time ago. And some would say that this is the first computer. It was solving the equations of motion of the planets. And it was used for either some sort of navigational or ceremonial process. Nobody really knows. The thing about this is science way ahead of any ability to manufacture it. So this guy pretty well had to make the metals himself. There wasn't files, there wasn't drills, there wasn't machine tools or anything like that. To create a machine like this literally meant making the tools to create the machine like this. It was a labour-intensive process, and it proved the concept. But it was far too expensive for anything other than special use. There was probably ever around 10 of them. Now, it wasn't actually until 1800 years later that the technology allowed that thing to be created. It looks slightly different, it's Graham's orrery, but nevertheless, as a concept, it was doing the same thing. He'd now had machine tools, though. He was able to use the technology to make this thing manufacturable. So there's a world of difference between what a scientist might prove and what a product might be, and the product is essentially linked to the ability to do it. Babbage's difference engine, another concept, 1837. Wouldn't it be nice if we could automate the production of tables? So he designed this thing. Tables, for those that don't know it, are the predecessor of the pocket calculator. Essentially because complex calculations were just too complex to do by hand, so you made use of tables to simplify the calculation. Now, as a concept, he was spot on. As a reality, he couldn't make it. He knew what the tolerances were on all of the machines and all of the cogs and gears that he would need to make it deliverable, but it was way ahead of the technology to deliver it. Amsler's planimeter, on the other hand, was a very good example. 1856, it's still going back quite a bit. This is a device for calculating the area of an arbitrary two-dimensional shape. Sounds quite easy as a concept to do, but look how neat the implementation is. You have this thing which you hold in one place, and you have this pointer which you move around. And as you move, you've got this gear which is slipping in that direction but rolling in the other direction, and there's another gear in the other for the other axis. It's a lovely example of making use of the technology that was available, because this thing was a success. In fact, so much of a success, they still use them today. Somewhat different variety, but if you look at this, essentially it's doing exactly the same thing. It's just that electronics have been introduced to improve its performance. It took it from a few percent accurate for this fella to quite a lot more accurate, around 0.2%. It's amazing, though, how many people, architects and the like, are using things like this, still use their grandfather's planimeter. I mean, can you imagine using your grandfather's pocket calculator? No, of course you can't. I mean, but this has a place. 2% accuracy is adequate for an architect. But in terms of the beauty of having this thing in a wooden box that you open up and you take out and you use, I mean, that's another form of engineering. But it's again, it's matching the technology with the capabilities. 1947, University of Manchester's baby computer, arguably the first general purpose stored program computer, again for general purpose solving, equation solving. General purpose equation solving tends to be thought of as computing, but actually computing also includes fixed equation solving. So the solving the equations for the motions of the planets, the equations don't change, but what you are actually doing is making use of a fixed equation and solving, let's say, where a planet combination is today. And so in this sense we've got two forms of computing. This one is the general purpose one. Again, the success of this one is really demonstrated by the computers that you see in your pocket today. But you wonder, why did they build it like that in racks using valves? And of course the answer was they didn't have any other technology. The engineers who designed it used the technology that was available to them at that time to produce as good a solution as they could, which is a creditable thing because that's what engineers should be doing. So I learned that implementations are limited by the available technology. So engineers don't use technology which isn't available, they use technology which is. Because business is about producing product, not about nearly producing product. So you don't sell a nearly produced product, you sell a product, and it's got to be there. That's an implicit part of this role that you've got to realise, because again, in the beginning, I've certainly been guilty of pursuing my personal agenda, my interest in technology and so on, and focusing on effectively excitement, whereas I should have been focusing on product, because product is the thing which was ultimately going to keep the business afloat, and in due course the business that I was in failed. It happens. It's really that bad. If a business is not profitable, doesn't have a future roadmap, can't make the things that it promises, it fails. Education establishments don't fail in the same way, so we should watch that. So what we can say about electronics then is it is a technology which has enhanced functionality again and again. So we're used to seeing these as examples of old computers. Anybody remember the Psion? Of course, they've all developed. They've become much more sophisticated. And again, we're used to seeing them. We tend to think of them as the same thing, but they're not. They're stages of enhancement of functionality, regularly improving. And of course, we're also used to seeing things that weren't even electronic at all becoming electronic. Can you imagine an electronic camera? Cameras don't need electronics. Thermostat. Who needs an electronic thermostat? Bimetal has worked beautifully for centuries. Why would we want to change it now? But we do. And of course it's Gordon Moore's fault. Well, it's not really his fault. All he did was notice, like Newton noticed gravity, Gordon Moore noticed that integration was actually quite a big force, and he hadn't really thought it out. But I mean, it was 1965, which is actually the time I left school. But he noticed then, he was a little bit older than I was, a bit wiser no doubt, and he had noticed that the rate of increase of complexity of integrated circuits, which was still very simple, was doubling roughly every 2 years. And he was predicting that by 1975, which is where the highlight should be, that there would be as many as 65,000 transistors on an integrated circuit. Could you imagine that? So by then, that was seen as some sort of major milestone. But you have to remember that he was designing with integrated circuits at that time with around 80 transistors on it. And he was basing his observations on the integrated circuits which it followed, which had 30 to 40 transistors on it. So what does a 40 device integrated circuit look like? Well, that's what it looks like. That's the EDA tools of the day, incidentally, because you didn't need anything else. It wasn't actually that complex to work out what the circuit did, and you multiply it by 4 and you've got around 40 components. And so That was what he was basing his observations on. It's hard to believe that integrated circuits were once that simple. Now, of course, Moore's law then, and there's no particular surprise to most of you in this room, has been doubling the number of transistors which are available for product functionality delivery. That's what it was. That's where the useful part of this comes in, on a roughly 18-month basis. Now, I mean, there must be a more useful or more up-to-date graph than 1999, but actually I like this one because it's got the red line on it as well, and I'll come back to that one in a moment. But if we just look at this, extending it to today is not such a big problem. But it's interesting to look at events on this graph, because in 1991, when ARM was founded, the typical integrated circuit had 1 million transistors on it. It's quite a lot more than the 50,000 that Moore was talking about. 1 million transistors seemed like a big deal. Today, we're talking billions. That's thousands of times more complicated. Well, thousands of times more complicated. 20 billion transistors that you buy every time you buy a small micro SD card. You're talking about buying a few billion transistors, most of which will never do anything in their entire life. The transistors have become throwaway components. You don't look at design anymore as transistors, you look at it as systems, as functionality. So 20,000 times the number of transistors on an integrated circuit between when ARM was founded and now, and running about 10 times faster. So that's 200,000 times increase in complexity between when ARM was founded and today. Now think about this, because this is a relatively short period of time. To me, 25 years is part of a working life. To most people, students in particular, they haven't had a working life yet. And so this idea of things going back in time is a difficult one to appreciate. But a lot of you have had this time, you've seen it, but you haven't really appreciated that that's the environment. That's why we've had to keep on training and retraining our engineers, and the engineers have had to keep adapting what they know and what they've been working on, because they've had to handle a design complexity which, even in the integrated circuit, is 200,000 times what it was just a few years ago when ARM started. So the NVIDIA Tegra, just to put some scale on this is not the latest chip, 2012, but it did tell us this is a typical device of around 1 billion transistors in that day. Now, of course, you can delve down inside, and you've all seen the micrographs. It's interesting to remember, though, that's 3 transistors of the billion, of the 1,000 million that are on that integrated circuit. And one thing to note here is, those are the transistors. Look at all this complexity up here. Nobody talks about that. The complexity of the integrated circuit is not the transistors, it's how you connect them together. And it's quite reasonable to expect there is another 100 or so factor of design complexity caused by the interconnectivity that you now have as a capability. Now, business opportunities drive technology, and I started off by saying how important it was that we understood this. Back here, 1970, 75-ish, most of the electronics was professional. 1975, here we are. It's that market gave us supercomputers, it gave us the basic mainframe computers, it gave us, well, it didn't really give us PCs, but it was certainly on the edge of that era. That market hasn't gone away, and in fact it's probably bigger than it was back in the 1970s, but it's not the major thing anymore. You can see as these eras go by that the major thing becomes something else. So the mini computer, the personal computer, they all started to come in, and one of the things that came along with that was increased volume. The volume at the end, over on the left axis, is very important because it tells you that the business interest is there. The professional markets are still there, but they have to now make use of the technologies which are provided by a lead market. They're not the lead market anymore. They're only a user of that market. Now, it will happen. I know it will happen. IoT, Internet of Things, is going to be the next new craze. Next new craze is going to be the lead market. It's going to be where the technologies are developed, how those technologies are going to be developed, where the investment in those technologies, and I'm not just talking about silicon, I'm talking about the technologies to deliver functionality. All of those investments will be justified because of the huge volume of these things that are going to be sold. And let's put it into context. That line represents 10 computers per person in the world. Now, we're not going to be selling these one at a time. We're going to be buying them in a bucketful. You're going to be buying them because they do something else for you. It's like that thermostat or your car or your TV remote control. These are things which are a lot more intelligent than they once used to be. And you don't buy them for the computer. What matters is the functionality of the box. One thing that it does see, though, is a change from technology for science, which is where we would like to be because we're all techies and we understand that, through to technologies for pleasure. So it means that the driving force is not the technology itself. The driving force is satisfying a human niche, a human itch. Now, we have an advantage here, and we could play it very carefully if we wanted to be, because although we're all techies, we are mostly all humans as well. It's up to you to decide whether you've actually got both of these facets, but most of us have. So we can actually look at these technology products as a human looks at it, or we can look at it as a techie looks at it. Now, that should give us an advantage, but we tend to separate these two things in our lives. When we buy a product from PC World, it's a product that we're buying. It's not necessarily anything to do with the work that we're doing on a daily basis, and yet it is part of the same life cycle, so we have to watch it. Move on from that. Now, becoming a little bit closer, because I wanted to try an illustration of the amount of change on a very much shorter time period. I mean, most people remember, even though they don't necessarily think about it, the time when cameras had film in them. It's not long ago. 1998, this was a Canon EOS Rebel G2. It was considered to be a really quite desirable low professional end camera. Excellent lenses, fine mechanical mechanisms, electromechanical exposure metering, which is pretty unsophisticated, metal and some plastic forming. It doesn't look very sexy in modern terms, does it? A little bit plastic. Photochemical memory. Interesting to think of film as a photochemical memory. It's also interesting to think of the processing, the computing that goes on in the lens. Because a lens is a very clever thing. It takes the entire 3D universe and it transforms it into a 2D universe, which it then maps onto a photochemical memory. That's pretty good, actually. And modern cameras are still the same in many ways. Here we are, a modern camera. It looks kind of better. It still is a mechanism for enhancing human memory. Its technology still has excellent lenses and displays and precision forming of metals and plastics, although the plastics are different and the mechanisms for forming them are significantly improved. But it's also very different. Digital logic in there, software memory makes it a computer, and this one is an ARM-based computer. But there is also analog electronics, sensors and transducers, precision mechanics, micromotors, batteries, energy storage, LEDs and discharge tubes. The precision forming of plastics and metals have changed remarkably, but is not appreciated. The electronic packaging, how do you assemble this thing? The answer is, unless you've got precision robotics, there's no way you can assemble it. So the manufacturing process has become an important part of delivering this product. Now, credit is due to Canon, because they were in the business of leading the photography semi-professional market, and they still are, and indeed they are now probably a bigger leader in the professional market than they used to be. Kodak, during the same time, went away because they focused on the film. They considered themselves to be the world leaders in photochemical memory. And credit for them, they could have got it right, but the bad news is they got it wrong. Now, it's awfully easy, because you could be a world leader in something today in business, and if you go in the wrong direction, then you're out of business and nobody's ever heard of you. So all of these technologies are available to everybody. So if all of these technologies are available to everybody, why don't other people go into the camera business? Well, the answer is, of course, that it's not just that they're available out there, they have to be available inside your company. Because the company can only use the technologies which it's got, or its designers can only use the technology their company has. It can't use the technologies it hasn't got. So the fact that somebody knows how to make lenses doesn't mean to say that I could make lenses. I couldn't. I can know some people who do, and I could use them to do it. But I think that's a subtle change in the way that business has evolved during this period of time. Because when I started, businesses tended to be all under one roof. Now you're working with a lot of other businesses to produce your product. So what it means, though, is electronic systems, which are what people buy these days, are not just electronics. So please don't just educate people on electronics. You've got to educate them on electronic systems. These other aspects are part of delivering a seriously competitive electronic product. But the interface is what the customer sees, and the wonderful way that you implement it, including the architecture and the mix of technologies and so on, is something which the customer isn't really interested in. It's whether you can make it at reliable quality and quantity, and whether the end customer is prepared to reach into their personal pocket and fork out their hard-earned cash to buy it. Now, there is an interesting thing starts to materialize here, because traditionally the bill of materials is a list of all of the components which go into a product. And these are physical, tangible components. Yet if you look at an awful lot of those, a lot of them are actually knowledge and know-how. Software, for example, is a component which is in that phone, and yet it's not listed on the list of the bill of materials, the list of physical components. ARM technology is in there, but it's not listed on the bill of materials, and yet is something which has a price. It's part of the manufacturing cost of making that phone. Whether it's amortized over all the phones or whether it's all lumped into a startup cost, who knows? It's still there. But what we're realizing is virtual components across the spectrum are an important part of products today, although most people still tend not to think about it. Reproduction, manufacturing, robotics, test. This never used to be a big part of the creation of a product. It's becoming a major consideration. So your electronics designer, the people who are designing these electronic systems, have to give consideration to how it's going to be made, how it's going to be assembled, how it's going to be tested. If you make this wonderful thing but you can't test it, it's not a product. People don't get a chance to buy it. So innovation now transpires to be the way that you, as a design engineer, architect the system. You want to produce the best possible set of features, valuable features, at the lowest cost, and that includes the cost of manufacture. And if your product is inferior to your competitors, it's frequently because you've got the architecture wrong. Innovation, it transpires, in my mind at least, without any doubt at all, is how you architect products. It's how you use what you already know how to do to create something which is mold breaking. So returning now to that second line. This one was known as the productivity gap, and back here it was a lot of talk was going on about that. We were seeing the EDA tools were delivering higher productivity, but Moore's law was delivering very much larger, more complex integrated circuits even, on a faster time pace. So the productivity gap was going up. Now back here, it was kind of affordable. It wasn't the end of the world. You did take your integrated circuit on a clean sheet of paper, and you did design it, and your productivity tools, you could actually achieve your next generation product just by doubling the size of your team. It was an attainable goal. But look at the numbers for years going out. We're talking thousands of man-years of effort. The other thing that was starting to make an appearance too was verification. It had never been a problem to verify a 4-2 input NAND gate integrated circuit. There is only 4 combinations of inputs for each of the NAND gate, and there are only 4 gates. Verification wasn't a problem. You could sit down in a lab, you could go through it all, and a few minutes later you say, yeah, it works. much, much more difficult to do as the complexity of the devices go up. So we were also seeing then that not only was the productivity gap going to be huge, but the verification gap was going to be even huger. So what happened to it? Because on that basis alone, we couldn't possibly have produced the integrated circuits that we do today. Well, the answer is that we started to do things that we didn't do in the past. So back here, and my first integrated circuit, I designed on my own. I did it all. It was all on a sheet of A0 paper. I used a logic template with a plastic pencil lead on it, and I drew the circuit of this small telephone circuit that I was working on. I did it on my own. Fairly soon, I needed to have a small team. Then the small team became, we're not just designing 10 integrated circuits in the company, we're only designing one. And it's the one that matters now, because we couldn't afford to put a large enough team onto this. We also moved very quickly to the global teams. You couldn't find enough people in England to do this anymore. You had to start using India, was very popular in those days, and America. So we acquired offices in those countries, essentially just to enable us to do the designs. Now, I'm not talking about ARM in those days. I used to work for another company. But the same thing has been going through the industry. What it's been meaning, though, is reuse has come in. We used to do designs by a clean sheet method. Practically nobody does anything by clean sheet anymore. You reuse. You reuse, in the first instance, some things. Later, hardware and software. Now, expertise as well. You're using companies who've got expertise in specific areas, and you're using them because they have that expertise. As a designer, as a system designer, you have to say, I'm not going to design my own CPU in this and make my own compiler. I'm going to use something like ARM. Here is a company that's got expertise. They will deliver me a block which I am very confident will go into my circuit. Not only into my circuit, but it will work in the system that I'm producing. That's something I don't have to worry about anymore. But it's not just ARM. They do this from quite a lot of IP sources, as they tend to be known these days. In fact, if you look at reuse like that, we're already well in excess of 90% reuse in our systems. Most of the systems, most of your smartphones and so on, are evolutions of what went before. Most of the software goes over. A lot of the hardware goes over. It may be a new implementation of a chip, but the architecture of that chip has stayed the same. But actually, quite unnoticed, since the 90s, designer productivity has been driving the methodology. The product possibilities offered by increasingly millions becoming billions of affordable transistors has always enticed the industry. My gosh, if we could do this with a few million transistors, think of what we can do next year with twice that number. Our product is exciting today, but next year it's going to be even more exciting. Now, it's an easy thing for a marketeer to say a more exciting product using twice the number of transistors. It's actually a quite different thing for the designer to have to make that happen. We've just doubled the number of transistors, but we've probably increased the design challenge by a factor of 10. Now, that's a thing which is let's say, fairly easily understood, but is not appreciated, because as far as the marketeer is concerned, we're just talking about a device which is a bit faster, or a device which uses a little bit less energy and the battery lasts a little bit longer. So the only possibility for achieving this in a reasonable time is this reuse. And I'm talking, though, not just about hardware, but software, methods, tools, internally and externally to the company. Reuse improves quality, because objects become designed more carefully. They're designed for use more than once. They don't just have to function that first time. Bug fixes become incremental. Things get progressively better. But there always are errors, and they have to be considered. But as a methodology, if you're going to teach people to design, electronic design, a large part of it is about architecture and is about reuse. I mean, yes, transistors are in there, but it's not the only thing that's in there. There are still examples, though. You can go that way. You can use your high-performance computer as an illustration of how wonderful your technology is that you want to use. But bear in mind, that's not where the majority of the market is. You will not find the opportunity for you to find exploitation for your research work unless it's aligned with something which has got big commercial opportunities, not just low-end stuff. Now, the other things that you find in this area are military and secure products as well. They can often afford to pay the significantly higher cost of getting something designed from the ground up. But actually, even they can't afford it for most applications these days. It's why a lot of them are now starting to use, and military started to use a little while ago, commercial GPS. Because actually, although it wasn't military rated, it was so cheap that you could carry a spare one around with you. It didn't need to be that reliable. And of course, every member of a troop would carry their own GPS. So if one of them failed, then you were still not going to be lost. Now, to put this in context then, when ARM started in 1991, this great idea that we had was to take this little thing. I'm not asking you to understand it, but anybody who's ever seen the inside of a computer recognizes that is the basis of a computer. That was the ARM7 processor that we had. The novelty was we would make it in an encapsulated way and make it available through a kind of Lego-like approach to make an integrated circuit. Nobody else was doing that. Now, that was the clever part. The technology itself, the process, the CPU, wasn't clever. It was only the idea of making it available so that somebody could put it into a circuit with their other components of their own choice. It was a revolutionary idea in its day. We're familiar with it now. It came about since I moved into the electronics scene, and indeed most people now are so familiar with it. Now, that integrated circuit was one of the first ones that was produced using that technology. So this was done by a company called GEC Plessey Semiconductors down in Plymouth, which happens to be where I live and where I used to work. And it was an example of taking that as a cell, bringing it into the company and sticking the other things around it. So it worked. It was a lot of difficulties. A lot of the things that we had to encounter had simply not been encountered before. But we got over it, and we did produce, at the end of the day, that particular processor. Now today, 2016, it's much more an issue of bringing the right horse to the right course. So we still have a processor, but I mean, this is an example of an A15, a much more complex processor. This has actually got 4 processors in it, so it's actually a mini network of processors in its own right. Then you've got the Mali suite, which are aimed at DSP and signal processing. These are different areas of general purpose computing. And we still have a very smallest processor, about 50,000 transistors, whilst these are 1,000 times bigger. So we're not just providing one processor anymore which goes into the market. We're talking about a range of processors. In fact, 24 in our current family. These are processors that you can go and you can buy, license, whatever the agreement would be, which will be focused, or let's say optimized, for the particular need that you've got. So a particular application that you need may be high on the DSP, low on the processing. The processing might need virtual memory, or it may not, and so it goes. So these are the processors in our family. But it's not just the processors, it's the methods and tools and utilities to build them into systems. Because the processors, as we've already found out, are just a tiny part of the whole, the tip of this particular iceberg. Architectures, so we've got to tell people and show them how to build complex systems. So here is a way that you put it together. You can array 4 quad cortex cores. That's 16 CPUs there if you want to. You've also got the GPUs, lost them temporarily, I'm standing too close to it, and the methodology for connecting it together to support debug in this environment. All of that had to come from somewhere. The simple single A7 core didn't need any of this. It was just a simple core. So all of this methodology has to come from somewhere. It's part of the product that we've had to develop, and it's part of the growing up of ARM and its engineers. And that's not all. The support for the design tools and libraries. Our IP exists in a design flow. It's in a design flow of people who are producing systems. They've got tools that they want to interface to. They've got other sources of IP that they want to incorporate. OSs being a particularly good example. We don't design any main system OSs. They're already out there. So Apple's iOS and so on are the property of somebody else. But they need to work on our hardware. So we have to support the porting of those. All of this, and the round numbers, 1,000 partners that we have in the design cycle, all of which need help and support to do what they do. This is the tip of an iceberg. And of course training, which is very applicable for today. We have professional training for those engineers who are already out there in the field, but we also have the ARM Universities program, who is focusing on trying to provide the material for educators such as yourselves to bring people to give them a soft lead into the ARM world. And I'm pleased to say that there is a booth in the room behind, and please drop by. Especially interesting is this lab in the box stuff. It does enable you to take commercial hardware, which is delivered free, a lot of access to a lot of good professional software tools, essentially our standard software tools, free, with all the documentation, including slideware that you can modify, masters, that you can modify to your own education purposes, drop them into your own slide sets, move them around. It's a great package. It should be a great package for you. Of course, it's a great package for us too. We want students. One of the things that we need as a growing company is an influx of new educationally prepared students who are going to be engineers in a couple of years' time. This is a good way of getting them into the right mode to be employed by ARM. Of course, the other thing that's changed, and it was fundamental in the beginning, was the business model. We had to have a business model which was going to be a viable one. And of course it is arguably a viable model. I think we can now look at it and say it works. Certainly in the beginning we didn't know that it was going to work. The idea of selling a block of knowledge to a company who was going to pay you money for it and were then going to give you some royalties with every device as it went out of the door, they just didn't want to know about it. It was only when they realized they had a productivity problem that they started to take it seriously. But there is a pipeline here. Our research is 2 or 3 years in advance, and then we have a development activity, again to produce something which is ready to go into a customer's design flow, because they want to be dependent on it, they need to be sure on it. It then takes 2 or 3 years for that to go through their own product development cycles. And they can frequently run on for 20 years, however. We have some products which are still running 20 years later, still a royalty feed for us. So it's a long pipeline. We're producing new processors at a beat of 1 a year at the moment, because that's the sort of pace that people expect it to happen. But the pipeline before those things actually come out of the door and appear in the products in your pocket, between 5 and 7 years. It's a long time. But here we are, 15 billion ARMS chips last year. 1,300 active licenses, nearly around $1 billion in revenue. We're 3,600 people, however. We're not the biggest company in the world, and we're spread around 36 offices. And for those of you who've never heard of us, of course, we're the leader in embedded computers, in all kinds of things that you don't even think of as being computers today, because people buy them for their functionality. 75 billion shipped since we started. That's a number, isn't it? 6 billion. More than 2 for every person in the world last year. And that's quite an achievement. So here I am then at the end, at my finishing line. Did I consider that my education prepared me for this? Well, actually, I think the answer was yes. Because although it gave me the basic language, it also excited me about it. Because it was the excitement that drove me forward. As I experienced this thing, I got more and more excited about it. It taught me how to work in a team. It gave me the scientific methods. And it did give me some useful background information. I've never designed RF, actually, but I've always found it useful to know some things about RF. And that really just stems back to my days in university, when we did actually have an RF design course. The rest of that evolution, and it was a fast evolution, happened on the job. And I reckon that around 50% of what I knew became less important during the last 2 or 3 years and was replaced by stuff I didn't know before. And I think that that's a high rate of learning. It is, broadly speaking, about the same level of learning as actually going on to an undergraduate course and doing another one every 3-ish years throughout your working life. It's certainly so important because of the levels of change. It needs to be managed. And it isn't terribly well managed at the moment. Now ARM, so I'm going to look at some of the educational stuff around ARM, because I think it's useful to know. ARM is a company. It's not exactly a typical company, because the employment profile, 95% of ARM's employees have got a first degree. That's quite unusual. Traditionally, factory-based industry, 95% of the employees you've actually taken from the streets and taught them how to do the job that they're doing within, I don't know, a week, 2 weeks. It's not a major thing. We're a knowledge company, and knowledge companies are probably where a major part of the contribution of this economy is going to come, the economy of Europe and the UK and probably the developed economies. 50% have masters, 9% have doctorates. A third of the acquisitions, third of the new hires come from acquisitions. We acquire companies who are going concerns, and we incorporate their technologies, their abilities into our company portfolio. And we bring engineers into the company as we do that. Around a third are experienced engineers, and around a third are new graduates. I'm separating those two. Very important. The person who comes out of university is not an engineer. He's a budding engineer, he or she. The experienced engineers are people who've been around the block a couple of times. They've experienced, they've bumped against things, they know some of the realities. They are very different people. Most businesses recognise that, and the first 2 or 3 years in post, they're treated as graduate engineers. They have an elevated salary increase over the normal working population, but they also have greater training opportunities as well. There's the mix: computer science, electrical, electronic, physics, maths, non-technical subjects. Now, we employ a range of people. Not everybody is going to do electrical or electronic engineering in ARM. There are people there who look after the IT systems. They're ARM employees as well. There are also people who are doing fundamentals associated with maths, associated with formal methods, for example. Other people who know physics very closely but don't actually know anything about electronics. But they are all necessary in this complete company. Main board directors, we're fairly unique in the sense that all of our main board directors are engineers, other than our CFO, who did history, so we've even got a history graduate in there. Company secretary is a lawyer. A general counsel was a chemist turned lawyer. This is amazing stuff, isn't it? I mean, this is probably one of the highest paid jobs in the company, and his first degree was in chemistry. And so he's a lawyer on the board. HR director was a material scientist turned HR. He actually couldn't handle the scientific aspect of it, so he thought that handling people would be easier. I don't know whether that's turned out to be true or not. You can all argue about the merits and demerits of HR departments. So essentially, all business needs a diversity of skills. Technology is just the predominant skill in a company like ARM. Now, I'm not going to go through that blow by blow, but it's just something you can look at later if you want to. But I realised that talking with my grandson, who was very small, about 4 or 5 at the time, he was bemoaning the fact that his sister, who was 3 years older than him, knew everything and he didn't know anything. And it really sort of registered with me that, primary education was about providing just enough information to get by in the world. That secondary education is really only bringing people up to an average level. That's its objective in life. It's only when you move beyond that point that people start to gain value which is greater than the norm. So at this part, they're a cost, definitely a cost. At this point, they're learning to be average. They can be an average contributor, but they won't be better than that. But when you move into this area, they're starting to be selected. They're starting to have skills which are much better and more valued if they're sensibly aligned. But whereas this is provided by society, this part of it tends to be quite neglected. It happens by accident. And yet it's a big opportunity for both the educators, but it's also a big opportunity for business. If business doesn't educate its people, then it has to recruit new ones. That's another way of looking at it, because the existing people are people it can use, and all it has to do is to re-educate them or improve that education a little bit to get a greater value out of them. Now it's down to my last couple of slides, probably okay. Elitism and engineering scientists. I mean, it's kind of acceptable that if you're going to be a weightlifter, then you have to choose your parents very carefully. You know, but it's not recognised that in an academic sense that this is an acceptable way of thinking. I mean, people are different, and I'm sure that you've discovered this. If nothing else, there are people who have affinities for arts and people who have affinities for sciences. And you can train people to be better at one of those things than they naturally are. But actually, unless you've got an affinity for it, they won't carry it forward. So I think that we've got to recognise that elitism is a part of being an engineer. And society has got to live with that. And just like it lives with the fact that not everybody can be champion weightlifters. But if you look at the numbers around this that I was able to see, around 3% of the population actually has an engineering degree, and only half of that number are actually involved in electronic systems roles. That's broadly equivalent to one person in the top group in an education class. So that is the geek. You know, you all know the geek. There was a geek in the class, and most of it was probably you, right? I think I was. That's tough being a geek, and it's tough being a female geek. So I'm not going to generalise on this. Females undoubtedly have a harder time in this world because being a geek is more embarrassing to them. But being a male geek is not a hell of a lot of fun either. Everybody does pick on you, but the good news is you can get your own back on them because generally speaking you're in a better job than they are. Only around 1% of those will be world-class leaders. That's 1 in 100 classes are going to produce somebody who's going to end up as a world-class leader. This is a huge opportunity. There are not very many of these, and yet there are a lot of contenders. There are people who are just a few % away from that. With a bit of encouragement, they could be world-class leaders. This is a huge opportunity for people like the government, because with a little bit of money spent encouraging the best, as opposed to derating them, then it would be a very sensible investment, because those few % of people have a very great contribution to the local economy. Alas, initiatives to realise the potential of 0.03% of the population will be seen by society as favouring the already favoured. You know, we are not to be encouraged, we're to be derated. We have to remember our school days. So does ARM have a problem recruiting engineers and scientists? No, it doesn't. But could we have a problem? Yes, we could. We don't need large quantities of people, but what we do need is the best. And we have already become a global company by acquiring the best wherever they are. So we've got 34 offices around the world, 7 of which are design facilities, proper design facilities. And those companies that were incorporated may have been brought locally, but probably have been developed where they are, have been developed because they had a skill that was valuable part of ARM's portfolio. We have lots of vacancies, around 265 today. And there's plenty of opportunities going on here. And we're growing as a business about 10% per annum. Numbers growing as a value about 20% per annum. So we're in a glorious position of being in a successful business. Successful businesses are not thick on the ground, but it does worth getting into. But 3,500 employees worldwide, 1,500 people in the UK. We're not going to solve the UK's employment crisis. We're not looking for people who don't know anything about anything. We're looking for people who are basically good. And you can't blame us, because our business is not charitable. Our business is about making money. It's about selling things, sophisticated technology things that people are prepared to pay for. So we are recruiting fast enough to meet our plans for organic growth. We do it via individuals, acquisitions, and by retention. As I said, retention is a good way of employing people, because if they don't go, that's somebody that you don't have to replace. So training is one of the big things that you do to keep people there. Fulfillment, give them jobs which they're good at, which is also mutually beneficial. You keep them, they're interested in it. You know, it's a good thing if everybody in the company actually enjoys what they're working on. It keeps them in the company and keeps the company going. Moving people around, we do that in the same way. We're quite happy to move people to other ARM offices in other continents. If it keeps them in the ARM fold and they're still doing something which is an important role for us. But there is opportunities, and I think that's the other point on this one. It's not just ARM. Other people can do this. ESCO is a report that was done a couple of years ago, and you can find it here. All these slides will be on the web afterwards. The ESCO report says, and you probably don't appreciate it, there are 30,000 electronic systems enterprises in the UK today. Mostly the only ones you hear about are Imagination Technology and ARM. Maybe a couple of other ones, small guys doing things. And you say, oh yeah, and there's them. Oh yes, and there's somebody else. 850,000 people employed. 5% of GDP is attributable to the work in this sector in the UK. And yet we're not valued. It's one of the biggest actual contributors to the economy as a sector, but it's invisible. So education then, from my view, requires a two-pronged approach. It's not just about educating the individual, it's also about educating society. We've got to tell society about what we do and how what we do fits into the whole. Because it's only then that they will say, my God, these guys really are clever. And it doesn't matter that we have that title, but it actually matters from a recognition from society. These guys are clever, and they're doing something that's important, and they're contributing to the economy. Because it's only when the parents see and believe that they will recommend their kids go that way. And their kids are the in-feed to you, and they're ultimately the in-feed to us. Of course, you've got the educating the individual, but you've also got to recognise that it's a through-life requirement. So, my last slide. Conclusions then. There shouldn't be any surprises in this. I think it's fair to say that electronics in 1974 is not the same as electronics in 2016. This domain has seen huge change every year, and there is absolutely no sign whatsoever that it's plateaued. So it will continue to do so. So the engineers that you are training, the budding engineers that you're training, will have to survive a similar level of change in their working lives. So you've got to equip them to handle that change and still be credible engineers as they're doing it. My most particular feeling is electronics design is now misleading. It's system design we're talking about. We're talking about design throughout the entire system to deliver products. And that's what we've got to be educating. Electronics is part of that. Embedded software is part of that. But it's not one thing or the other. It's a combined thing. The design engineer's role, surprisingly, is still the same. Although the technologies have changed, the designer is still trying to produce effective product. So the good news about that is you can actually teach the principles of design without having to worry about the technologies which are applicable to it. It's the why you're doing it. It's the knowledge about the technologies and methods. It's architecting. How do you put these things together with the context of the bigger system? It's the optimization of that mix of technologies. You can put together a smartphone with a number of different architectures, but they have a cost as well as a value. The design engineer must learn to adapt. And the design engineer today will almost certainly always be part of a team, unless you're talking about a very small guy who's making a timer which happens to be used for something in a circuit and he's going to be manufactured for 20 years. He might do the whole design himself. The majority of the design engineers will be in a team. They still have to understand their role in the team, and the architecture aspect still applies to them. They have a specialization, because they shouldn't be in the team if they don't. That area may be test, it may be verification, it may be transistor level design, whatever. There will be administrative or specialised career path choices to be made throughout. You're always given the opportunity. A phrase, have you had enough of engineering? Do you want to go into a management role? This happens on a regular basis. It actually costs a lot to stay being an engineer. It's hard work, but it's enjoyable work if you're that way inclined. If you're fed up with trying to keep pace with this thing, then there is almost always an opportunity to move into the administrative groups. So it's not a once and for all. The design engineer carves him or herself throughout their professional life. So you're not the product of a mould, that's for sure. You're the product of an education which is a life's education. Higher education prepares you for this lifelong education. It doesn't give you the education, it gives you the good start. At which point I'll thank you and finish my talk. But if anybody's got any questions, feel free.
Thanks very much, Ian.